If an alien intelligence were monitoring our planet from afar, it might have misinterpreted the cataclysmic event of January 15th as an act of planetary warfare, a deliberate and colossal display of force. Since the latter part of December, the Hunga Tonga Hunga Ha'apai volcano had been demonstrating significant activity, punctuated by a sequence of rather powerful eruptions. On the 14th of January, local scientists witnessed it erupt yet again. This apparently immense eruption launched a plume of ash 20 kilometers into the sky, creating a gigantic pillar that ascended far beyond their field of vision. This, however, is all a question of scale. The breathtaking spectacle from the surface appeared as just a minor plume when observed from the vantage point of space. On the subsequent day, an event of truly monumental proportions took place. This next eruption, documented by both the GEOES and Himawari 8 geostationary satellites, may very well be the most powerful explosion ever captured on video. Preliminary assessments suggest that this event could eclipse even the largest man-made nuclear detonation, and it is not hard to see why when considering the sheer scale of the ash cloud. If we were to place it over the continent of Europe, we could see that it blankets an incredible expanse of territory. Our apologies to Luxembourg, which is not visible in the satellite data, but was picked up by instruments listening for radio waves. More than 200,000 lightning strikes were tallied within the plume. The phenomenon of volcanic lightning is still a field of active research, and the precise mechanisms that create it are not fully understood, largely due to the inherent difficulties of studying it up close. Nonetheless, scientists are starting to theorize that positively charged particles are generated by the eruption itself, in conjunction with interactions between the ash and the ambient atmosphere. Although the volcanic island itself was without inhabitants, the neighboring islands certainly experienced damage. The harm from a volcano comes in many forms, with the most conspicuous being the ash cloud. The islands nearest to Hunga were completely covered, with some media outlets describing them as resembling a desolate gray moonscape. On these islands, now coated in a fine layer of ash, before and after satellite imagery powerfully depicts the consequences. Residents in these vicinities were instructed to stay inside while the ash settled, as its inhalation can lead to significant pulmonary damage. Ash has also coated freshwater sources, rendering them contaminated and transforming what was once a lush and lively landscape into something that looks like an image, with its color saturation turned all the way down. In the short term, this is harmful to vegetation because it prevents sunlight from reaching the leaves. In the long run, however, it will be advantageous for the island's soil, as volcanic ash serves as a natural fertilizer, rich with numerous essential minerals. The finest ash particles, however, did not just travel horizontally across the atmosphere. They also unquestionably made their way into the stratosphere. As a general rule, the Earth's troposphere and stratosphere do not mix together well, which means that if ash gets into the stratosphere, it will remain there, circling the globe for a period ranging from months to several years. The most minute ash aerosols carry sulfuric acid, hydrogen sulfide, and hydrochloric acid. Intriguingly, this could produce a minor cooling influence on the Earth as a whole, because sulfuric acid, for instance, is known to reflect solar radiation back out into space. The negative effect, however, is that these particles will ultimately drift down into the troposphere, returning to the surface in the form of rain droplets, which is to say, as acid rain. The subsequent phenomenon you would have witnessed is the astonishing shock wave that radiated from the volcano. This mesmerizing visual is most readily seen in the infrared part of the spectrum, since infrared radiation is better suited for detecting the slight variations in atmospheric temperature produced by the pressure wave. This pressure wave moved at a velocity greater than the speed of sound and created a tremendous amount of noise. This footage provides some sense of the incredible power of this shock wave as it passed an island situated 65 kilometers away. To be honest, we can be grateful that no one's eardrums were ruptured. Even so, there have been reports of windows in homes being shattered by the force of the shock wave. This pressure wave is believed to have traveled around the entire planet at least 4 times, as recorded by weather stations in multiple countries. Throughout the United States, the shock wave was not audible, but its passage was noticeable as small shifts in air pressure as it moved across the nation. The shock wave was, however, audibly heard in locations as far away as New Zealand and Australia, and even as distant as Alaska. Typically, underwater volcanic eruptions are not known to generate tsunamis. However, due simply to the incredible size and abruptness of this specific explosion, it did in this case create a tsunami, although it was not an exceptionally large one in the end. It was nonetheless powerful enough to cause some destruction throughout the Pacific. For coastal areas located across from the eruption, upon hearing news of a possible tsunami, boats and other vessels were directed out to sea to meet the wave head-on. As tsunamis get closer to the shore, the wave's amplitude increases, making it much more prominent than a tsunami far from land, which is why the wave looks so massive here. These vessels are not an extreme distance from the coastline. The last type of damage I would like to explore concerns the volcanic island itself. This island is exceptionally young, having only formed in the year 2014. This is because it sits directly on the Pacific and Indo-Australian convergent plate boundary, an area known for its considerable tectonic activity. Before 2014, it was composed of 2 mostly submerged islands, with the caldera situated roughly 150 meters beneath the sea's surface between them. In the years since, eruptions had filled in the gap, connecting the 2 islands into one. As a result, it has even been the subject of study by NASA to better understand how water affects volcanoes, as a great number of ancient volcanoes on Mars would also have been surrounded by water. Scientists were hoping to monitor the erosion of this newly created island, which appeared within the ocean, to see if there were any similarities to the erosion patterns seen on the littoral fields of Martian volcanoes. This could offer further proof that some Martian volcanoes were also once surrounded by oceans. It is also compelling for scientists to be able to precisely gauge the extent to which similar planets like Earth and Mars truly are alike, their differences notwithstanding. Regarding Hunga Tonga Hunga Ha'apai, the ash that first created the island was readily carried away by the gentle lapping of the seawater, much like a sandcastle giving way to the advancing tide. But after about 6 months, the erosion stopped as the ash and seawater reacted to form a more durable, resilient kind of rock. If volcanic activity had ceased for good, Hunga Tonga Hunga Ha'apai probably would have remained as a small island for many more years to come. Nevertheless, the immense power of the January 15th eruption has utterly obliterated the island. What was a single unified landmass just last year has now reverted to being 2 separate islands, with the caldera once more sinking beneath the ocean surface. Yet, just envision if, someday, Earth were to suffer a fate like that of Mars, with its oceans completely evaporated. What we now perceive as a small island would still stand as a formidable 2,000-meter-high mountain rising from the ocean floor. While the volcanoes on our world are quite intimidating, you can find some solace in the knowledge that an explosion of this size could have resulted in far more devastating outcomes for us humans. Furthermore, this specific island will remain under observation by NASA for many years, helping us understand not only our own world but also our celestial companions in the solar system. And why is this important to us? Well, volcanic events on this scale can produce global effects, and by examining their interactions with our atmosphere and oceans, we can not only help forecast our future, but also glean insights into the past of planets such as Mars. Picture, if you will, that you are in your home or at your office when the very walls of the room you are in start to shake with great violence. Books are thrown from their shelves and cabinets seem poised to fall over. You realize immediately that this is an earthquake. Then you look up, and the thought strikes you that there is an entire other floor of the building above you. As the walls continue to shudder dangerously, you understand that if they were to give way, the ceiling above would come crashing down, putting you in extreme danger. And so, you keep looking upward as the shaking goes on, wondering if the building is going to hold. When you observe the video from the Japan 2024 Noto Peninsula earthquake, which happened in the afternoon on New Year's Day while families were together in their homes, it is simple to imagine the sheer terror that must have consumed those who lived through it. This was a lethal disaster, causing 241 deaths and 596 injuries. Despite its relatively small land area, Japan is the country with the fourth highest number of major earthquakes in the world over the last few decades. Our planet Earth is often disturbed by earthquakes, but there are certain features that set the Noto event apart from any other earthquake we have witnessed before. It is not at all shocking that Japan is frequently impacted by earthquakes. Japan is located on the western margin of the Ring of Fire, which is one of the most tectonically active areas on our planet. These massive lithospheric plates of rock and soil are constantly and unceasingly moving over millions of years, sometimes pulling apart and other times pushing together. To make things even more complex, Japan sits along the boundaries of several smaller plates at the same time. The Pacific Plate moves westward and subducts or goes under the Philippine Sea Plate and the Okhotsk Plate. But the Amurian Plate is also pressing against the Okhotsk Plate, while the Philippine Plate goes under the Amurian Plate and the smaller Okawa Plate simultaneously. It is a complicated geological contest, one that was responsible for creating the Japanese islands to begin with, but also one that builds up significant friction and stress beneath the ground. What occurs when the forces involved grow too strong for the friction holding them in check, and something gives way? That is the moment an earthquake happens. Nonetheless, in the case of the Japan January 2024 earthquake that affected the Noto Peninsula, it caught local people off guard. Why? The reason is that Noto is not actually situated on one of the primary fault lines, and scientists are still not completely sure why earthquakes are even happening there. If you were to map the locations of earthquakes by their depth and geographic position over the past 25 years, you would see that they mostly group together on the eastern side of Japan, which is where the Pacific Plate subducts beneath the Okhotsk Plate. You can even make out how earthquakes located farther to the west are also initiated at greater depths underground, which shows that the subducting plate has gone deeper into the Earth with the extra distance. However, rather than occurring on the eastern side of the island, the January 2024 earthquake struck Noto on the west. There are additional oddities. Strange things have been observed beneath Noto for the past 3 years. Since 2020, Noto has been subjected to tens of thousands of small earthquakes in a geological event referred to as an earthquake swarm. Contrary to what one might think, this continuous rumbling is not usually a reason for alarm, as having many small tremors is better than having one large one. And earthquake swarms typically fade away quietly instead of leading up to major earthquakes. Noto's earthquake swarm went against scientific models, lasting for an unusually extended period and giving rise to the incredibly strong January 2024 earthquake, and scientists do not fully understand the reasons for this. The consequences were grave. The January 2024 earthquake had a magnitude of 7.5 and occurred at 4:10 p.m. Japan Standard Time on New Year's Day, a moment when people were assembled in their houses. It was not just a single occurrence, but was joined by a multitude of foreshocks and aftershocks, numbering 1,200 in total, spread across an area of more than 150 kilometers. At least 7 of these had a magnitude of 5 or greater. 40,000 residences immediately went dark, roads fractured, and buildings collapsed. The Japanese government quickly put out a tsunami warning for the entire west coast of Japan, with the first waves reaching Suzu just a minute later. A wave reaching as high as 5 meters was predicted, although most of the video recorded shows a wave that was only 1 to 2 meters tall. Without a doubt, the power was enough to carry away buildings situated on the coast. In all, there were hundreds of deaths and more than 1,000 injuries in 6 prefectures, and property damage exceeded $18 billion US. The very land itself jolted and heaved. One strange feature of Noto is that a mysterious upwelling has been taking place there below the Earth's crust since the earthquake swarm started in 2020. The edge of the peninsula has lifted by roughly 3 centimeters since that time, suggesting that something was building up under the surface, possibly water, possibly magma. Scientists are not entirely sure. When the earthquake itself happened, however, that is when the peninsula really started to rise. Certain portions of the land were lifted by as much as 4 meters, and these changes are plainly visible in satellite pictures. The change in the land's height altered where the sea touched the shore, forcing the coastline backward by 250 meters and leaving some harbors completely disconnected from the water. And when that much land is displaced, it can affect the rotation of the planet itself, altering the distribution of mass on the planet's surface, which then impacts how fast it spins, similar to a ballerina pulling her arms in to rotate more quickly. In 2011, the magnitude 9 Tohoku earthquake in Japan made Earth's day shorter by 1.8 microseconds, or 1.8 millionths of a second. It is not a large amount, and other things, like different sea levels, also change the Earth's rotational speed, but it is incredible to see how interconnected the planet truly is. An earthquake in Japan can have a subtle effect on the whole world. Regardless of where you are, your life was altered in an imperceptible way by the Noto earthquake. Considering all of this, it is not at all surprising that scientists around the world are working hard to figure out what causes earthquakes. However, for those who live with their constant threat, such as the people of Japan or other countries like Indonesia, China, or Iran, it is just as important to protect against their effects. Therefore, in an effort to improve architectural design and make buildings more resistant to earthquakes, Japan's National Research Institute for Earth Science and Disaster Resilience has taken steps like creating the world's biggest earthquake simulator, e-Defense. This 20 by 15 meter shake table can hold buildings up to 10 stories high and can use real-life data to replicate the most destructive earthquakes Japan has ever faced. By evaluating various designs in different earthquake situations, architects have managed to create braces, beams, and metal joints that strengthen traditional Japanese houses, making them better able to withstand seismic shaking. This can be the critical factor that determines whether a building stays standing or collapses completely. Interestingly enough, NASA's space program indirectly helped in the development of earthquake-resistant buildings in Japan. Take the Tokyo Skytree, the tallest tower in the world at 634 meters, a building I saw for myself during a trip to Japan. Given the earthquake risk in Tokyo, it was crucial that engineers created a building that could handle significant shaking. They achieved this by including a central 360-meter-tall concrete column that sits on 4 huge rubber bearings, which are connected to the surrounding building with fluid dampeners that were developed during the NASA Apollo program. When an earthquake occurs, these fluid dampeners make the central column sway at a different frequency from the building's outer structure around it. The differing rhythms of movement cancel each other out, greatly lessening the overall motion inside the building. Amazingly, these effects can decrease the power of earthquakes by as much as 50%. Earthquakes can take a horrific toll in terms of lives lost and homes and livelihoods ruined. For the Noto Peninsula, its residents have slowly started the difficult process of putting their lives back together. Although the damaged roads at first made it hard for emergency services and repair crews to get in, power has been brought back to most of the 40,000 affected homes. However, as of March 2024, 790 still did not have electricity, 18,880 were without running water, and 11,400 people were still in evacuation centers in Ishikawa Prefecture. Earthquakes are overwhelming displays of the tremendous natural power that is always present beneath us. They can destroy cities, and recovering from them is a long and difficult process. But it is a testament to the resilience and willpower of the people who call places like Japan their home. They work to find solutions to powerful earthquakes, to forecast them, and to reduce their damage with clever engineering. This can help all of us together. By studying the processes that happen under our feet, we can better manage the world we live in a way that lets us thrive. The world is dangerous, but also beautiful. And like life itself, its face is always changing. It is our responsibility to face that change until we can overcome any disaster that comes our way. In the last few years, scientists have recorded a wide array of strange atmospheric events on Earth that were either not confirmed before or were completely unknown. These encompass transient luminous events such as red sprites, blue jets, gigantic jets, and elves. There are also noctilucent clouds and seldom-seen variations of common phenomena like green lightning and red auroras. These are only some of the amazing occurrences we have managed to see and verify. And yet, despite the incredible progress in our technology and research abilities, there remain phenomena that are almost entirely outside our capacity to prove with certainty. Among these, none is more strange and frightening than ball lightning, a purported electrical event so completely baffling that it sounds, frankly, made up. Ball lightning has been cited so many times and has received such widespread scientific attention that it exists in a strange space between scientific investigation and folklore. However, unlike the majority of myths, ball lightning is backed by an increasing amount of evidence that indicates we should not only give serious thought to its existence, but that we might already have proof of its reality. So, what is ball lightning precisely? How are scientists working to recreate it in their labs? And if it is, in fact, a real phenomenon, as many specialists think, why is it so remarkably hard to prove? Come with me today as we delve into the fascinating history of ball lightning sightings, look at some of the most compelling new theories being investigated now, and find out about amazing laboratory experiments that are working to solve one of science's most mysterious unsolved puzzles. For hundreds of years, stories of ball lightning have come from every part of the world. The accounts differ, yet many agree on specific points. The phenomenon shows up as a bright, glowing sphere, sometimes as small as a golf ball, and other times much bigger, It is usually said to be white or blue, but it can also be red, orange, or yellow. The phenomenon is said to last for anywhere from 1 to several seconds, floating on a slow path, sometimes changing its course, and at times even moving erratically. It has even been claimed to go through walls and windows without suffering any damage. According to some accounts, ball lightning just fades away, while in others, it explodes with great force, creating serious damage and leaving an odor described as sulfurous. At its most destructive, ball lightning has purportedly injured and killed people and destroyed strong walls, doors, and ships. Now on this channel, we do not take anecdotal evidence as solid proof, no matter how convincing it might be. Only controlled observation, strict testing, and repeatability can give scientific confirmation to a phenomenon. So, keeping that in mind, let's look at a few of the claimed ball lightning sightings that I find most fascinating. In 1739, the ship Catherine and Mary was sailing along the Gulf Coast of Florida when it ran into a deadly thunderstorm. According to someone who saw it, a large ball of fire fell from the element and split our mast in 10,000 pieces, killed one man, another had his hand carried off, and had it not been for the violent rains, our sails would have been a blast of fire. That is quite a story, but it gets even stranger. In 1753, Georg Richmann, a famous professor and electrical researcher, was at a meeting in St. Petersburg when he saw a storm coming. Taking an engraver with him to record what he saw, he hurried to do a kite experiment, much like the one Benjamin Franklin had done the year before. As the engraver later reported, Richmond was doing the experiment when a fiery blue sphere came down the string, striking him dead and knocking the engraver out. The reported autopsy showed a red mark the size of a coin on the professor's forehead and injuries that matched electrocution. But maybe the most convincing eyewitness story comes from 1963, when R.C. Jennison, a researcher from the University of Kent, was on a late-night flight from New York to Washington. Jennison was in the cabin just after midnight when the plane was surrounded by a bright electrical discharge. In a matter of seconds, a bright glowing sphere about 20 centimeters across came out of the pilot's cabin and moved through the whole length of the airplane. In 1969, Jennison wrote about what he saw in great detail in the pages of Nature magazine. Because of believable reports like Jennison's, scientists have taken this phenomenon seriously and have suggested many models to explain it. One theory suggests that ball lightning could be a hallucination brought on by the magnetic field close to a lightning strike, pointing to similar hallucinations seen during epileptic seizures. This theory proposes that ball lightning could be a creation of the stimulated occipital lobe. However, if this were true, it would seem to contradict the reported damage caused by ball lightning, like the death of Georg Richmann. Another idea suggests that ball lightning is a self-contained plasma reaction, similar to St. Elmo's fire, the phenomenon famously seen on the masts of ships when the voltage difference between the air and the ground is strong enough to break down air molecules into highly excited particles. According to this theory, the plasma inside ball lightning creates a self-contained bubble that acts like a soliton, a self-strengthening wave that keeps its shape and moves at a steady speed. Don't worry if you find this confusing. We are getting into a rather complicated topic that even scientists are still trying to understand. One of the most promising ideas was proposed by John Abrahamson and James Dennis at the University of Canterbury Christchurch back in the year 2000. This model puts forward that a strong positive lightning strike can turn molecules in the soil into vapor, creating energized nanoparticles that then combine with oxygen in the air to make light and heat. Remarkably, this model is backed up by a strange event that happened 10 years ago in Lanzhou, China. Remember when I said that there were no confirmed recordings of ball lightning? Well, that might not be completely true. In July 2012, researchers from Northwest Normal University had set up spectrometers to record normal lightning when a powerful lightning strike created a glowing white sphere. The sphere was thought to have a glow 5 meters in diameter, which became red as it moved for 10 meters before rising into the air. All of this was filmed with high-speed video, which unfortunately has not been shared with the public, and the spectrometer reading, which has confirmed emission lines from silicon, calcium, and iron, all of which are common in soil. Therefore, if this observed event was really ball lightning, as it seems to be, then it gives strong proof to support the vaporized silicon idea. However, this model does not explain certain behaviors described in ball lightning sightings, such as the ability to go through solid objects. So what does this mean? Well, either those stories are not accurate, or ball lightning could actually be a group of different phenomena. Besides suggesting theoretical models, scientists have tried to create ball lightning in labs with amazing outcomes. One experiment at the Max Planck Institute reported making a ball lightning-like effect when scientists discharged a high-voltage capacitor into liquid water. In 2006, researchers at Tel Aviv University did an experiment by aiming a microwave drill, made of a magnetron and a microwave beam, at a piece of solid silicon. When the researchers pulled the drill away, the drag made a tiny ball of plasma, almost exactly like the descriptions of ball lightning. An amazing result for sure, but is this lab-made phenomenon the same as those seen in nature? It is very likely, but right now, we just do not know. Another experiment done in 2018 produced even more incredible findings. Using advanced experimental engineering, physicists were able to create a skyrmion of Shankar, a quasi-particle that looks like a tangled three-dimensional magnetic field. Without getting too complicated, what the researchers did was apply an outside magnetic field to a system of rubidium atoms near absolute zero. The magnetic field made the atoms all spin in the same direction on the knot surface while twisting strangely on the inside. In short, the magnetic field kept a stable spherical shape, able to do things like squishing or changing shape while still keeping its main properties. This discovery could have big implications for quantum computing, but researchers also think the synthetic magnetic field. They made models the expected electromagnetic field of ball lightning. This theory will need a lot of follow-up research, but it is a promising discovery that could explain some of ball lightning's reported features, like its ability to go through solid barriers. So there you have it, a look at the incredible history of ball lightning sightings, as well as the advanced research that has gotten tantalizingly close to proving it exists. So, what are your thoughts? Do you find any of these theories convincing? Have you or anyone you know ever had an experience with something that looked like ball lightning? I would love to hear about it in the comments. All the best, and until we meet again. Australia has always been known for its hot weather, but when you mix record-high temperatures with a long-lasting drought, the outcome is what you're left with, a colossal wildfire with a smoke plume that travels for thousands of kilometers, easily seen from the Himawari satellite in orbit, and together we will see how this fire grew from December 30th to January 3rd and look at the effects it has had on Australia and the areas around it. Australia's weather has consistently been mostly warm, with a large part of the continent being classified as desert. But as you travel farther to the east, Australia generally gets wetter because of the mountain range that forces moist air to higher elevations. This means that eastern Australia usually has a more moderate climate. Nevertheless, in November of 2019, very dry conditions meant that even the plants in these wetter regions were completely dried out, putting the area at a greater risk of fires. As a result, catastrophic fire warnings were issued for 7 regions of Australia, including the greater Sydney area. Fires had been burning in Australia exceptionally early, and by November the fires had burned more hectares than the Californian and Amazonian wildfires put together. By late December, the drought had not ended, and Australia was about to face one of the most severe heat waves it had ever seen since records were kept, with average temperatures going over 40 Fahrenheit across the continent. In these conditions, fires can start on their own, and the saying, "spread like wildfire," really applies here. This is the way the event happened. On December 30th, smoke from the fires could already be seen from space. Its distinct brown color made it different from the nearby water vapor clouds. The fire kept burning all through the night, and by the next morning there was already a clear increase in its size. It was on this day that the Army was sent to some isolated areas to help with the evacuation of trapped civilians. The smoke plume now extended across the Pacific Ocean for at least 1,000 kilometers. Fires continued through the night, and in the morning, it was clear that the wind had changed direction, pushing the smoke in a more easterly path, completely covering the neighboring country of New Zealand. For context, Sydney is located around here and was also totally hidden by smoke. This greatly lowered visibility and also worsened the air quality for people to breathe. Sydney had the poorest air quality of any city in the world during this time. The last day of this time lapse truly shows the worldwide effects of such an event. On this day, the fires were still active, and the smoke from 4 days before was still present in the air, even after spreading out some. The smoke plume was now thousands of kilometers long. The fires have lessened somewhat for the time being because of the long-awaited arrival of heavy rain. However, the danger of more fires of this size has been predicted for the near future unless more rain comes. Wildfires are certainly a natural event in Australia. They have always occurred and always will. The climate is favorable for such events, and in some situations, they can even be helpful. But what are your opinions on the effects of fires of this size, and have you ever been personally affected by wildfires? I would be curious to hear your views in the comments. Just try to keep it brief. In total, during this season so far, 10.7 million hectares of land were scorched. Putting aside the human, biological, and political effects these fires have had, as that is somewhat beyond the focus of this channel, what I find most fascinating are the weather systems that developed inside this smoke. Most people know about cumulonimbus clouds, huge thunderstorm clouds that are made from water vapor. With the existence of such thick smoke, pyrocumulonimbus clouds have formed, which come with their own thunder and lightning. If you believe that normal storm clouds were impressive, pyrocumulonimbus clouds have a strangely unsettling quality. Also seen were fire tornadoes, which are tornadoes created from quickly rising heat and air. Another effect of fires of this size is the higher levels of particulates and gases put into the atmosphere, such as carbon dioxide and carbon monoxide. NASA's Aqua satellite has provided data that shows the carbon monoxide particles getting away from the carbon sinks of Australia's forests. Carbon monoxide is incredibly poisonous to animals and humans, just one of the dangerous byproducts of fires. Australia, like many other places in the world, has always had wildfires, and they always will. The climate is right for such events, and in some situations, they are even good. But what are your thoughts on the effects of fires of this size? And have you ever been personally affected by wildfires? I would be interested to read your views in the comments. Picture for a second that you are looking out of your window when a single very bright light suddenly appears in the sky right above you. This brilliant star is as bright as the full moon at night, maybe even more so, and can even be seen during the day. If you can see the light, you might already be in serious trouble, as that new star is now flooding the Earth's atmosphere with a disastrous amount of gamma radiation and X-rays, destroying our ozone layer and leaving us open to the full force of the sun's deadly radiation. On top of that, a massive wave of stellar material and debris thrown out at speeds between 10,000 to 40,000 km/h is rushing toward our planet. This is the last cry of an exploding star, throwing billions of tons of burning mass in our direction, ready to wash over our planet's surface in a fiery wave. This is a supernova, or at least it is one idea of what we might see if one happened close to us. But how likely is it for this to really happen? What is considered near us on a cosmic level? How close would a supernova explosion need to be before life on Earth was in danger? What might we on Earth actually go through? And which stars close to us have the possibility to explode in this way? Join me today as I talk about an event that could be an Armageddon in our time, or could be just a pretty light in the night sky. Let's start with the positive news. Supernovae in our galaxy are not a common event. While astronomers see hundreds of supernovae every year outside our galaxy, this is mostly because of the huge number of galaxies in the universe. Closer to us, though, inside our own Milky Way, we probably only see about 2 to 3 every 100 years. This means that the chance of one exploding tomorrow is not very high, though it is not zero. And according to archaeologists, Earth has probably been hit by a supernova before in its 4.5 billion years of life. For one thing, we live in an area of space called the local bubble, a fairly empty region of interstellar space about 1,000 light-years wide that is thought to have been created by a supernova explosion 10 to 20 million years ago, an event our planet would have been around for. I talk more about that in another of my videos, which you can find here. Scientists have found proof of another explosion that happened 2.5 million years ago, shown by a high amount of iron-60 and manganese-53 in a certain layer of the geological record. This supernova happened far enough away to be safe for us, but this might not always be true. Some scientists think that the extinction of woolly mammoths was due to a huge piece of debris from a supernova hitting the planet about 13,000 years ago. The supposed impact site had magnetic spherules and radioactive potassium-40, a material found in supernova ejecta, a smoking gun in the time most mammoths disappeared. Even before that, mammoth tusks from 34,000 years ago were found with tiny impact craters from grains of slightly radioactive iron that had been moving at 10,000 km/s. If you remember, that was one of the possible speeds at which supernova explosions move. That couldn't have been a nice experience for the mammoths involved. A sharp observer might, however, figure out an important fact from this. Clearly, if life started on Earth about 3.7 billion years ago, and we have gone through 3 supernova explosions that have affected us in the last 20 million years, and life is still mostly doing well, my sympathies to the woolly mammoths if you did die from one of these, then supernova as a whole can't be as destructive as my opening made them seem. And that is mostly correct, although it is, of course, a question of distance. If I am 1,000 kilometers away from a nuclear explosion, I have not much to worry about. But it is a different story if one goes off on my coffee table. And when talking about supernovae, it seems that the universe has some pretty big coffee tables. To understand the size of these explosions, it is vital to know the forces at play, which means we need a better idea of how supernovae happen. It turns out that stars can take 2 main routes to get to that explosive end, although in every case, it must be the right kind of star. For the first route, which leads to a Type Ia supernova, it usually needs a white dwarf in a binary system that is slowly or quickly taking matter from its partner star until it reaches a point of critical mass. This route is not completely understood, but it is thought that a white dwarf, or a dense star, made mostly of carbon in a huge superdiamond core, is usually perfectly balanced between two strong opposing forces: electron degeneracy pressure and gravity. This just means that atoms usually resist being squashed too much. Their electrons like to stay at certain distances from the atom's nucleus and will fight being pushed to a higher density. However, gravity is an extremely strong force that tries to pull matter closer, especially in a dense mass like a white dwarf, where a piece the size of a sugar cube has the mass of about a car. And in a binary system where the white dwarf is taking in more and more matter from its neighbor star, gravity eventually beats electron degeneracy pressure, and the whole thing collapses at once. Carbon fusion starts, and in a few seconds, most of the star goes through fusion, turning into heavier elements and letting out a huge amount of energy as the matter in the star settles into its slightly more efficient new form. How much energy? About 1 quadrillion joules, that is, 1 with 45 zeros after it. If you say you knew that number before, you are almost definitely not being truthful. All of this energy is let out in just a few seconds, so of course the star throws all its contents outward in all directions, pushing it at 6% the speed of light and letting loose a flood of mostly gamma radiation across the galaxy. The brightness of this event is 5 billion times brighter than our Sun and lasts for a few weeks until the ejecta has moved far enough that the overall energy level has started to go down. The second kind of supernova, type M, is similar, but instead of a white dwarf, it involves a huge star at least 5 times more massive than the Sun at the end of its stellar life. These stars are still shining intensely, and instead of just electron degeneracy pressure, it is also the heat made by fusion that keeps the star's balance. However, just like a type Ia supernova, the balance eventually breaks. This time it is because the star runs out of fuel, and without this extra fusion energy pushing the star's mass outward, electron degeneracy pressure alone can't fight the star's huge weight, leading to a similar result. The only difference is that while some of a massive star will remain, often collapsing into a neutron star or a black hole, white dwarfs usually disappear completely. In either situation, the amount of material and energy let go by supernovae is huge, so huge that, not surprisingly, anything in its immediate area will not survive for long. This is energy strong enough to rip apart a star. A planet would have no chance if it were in the immediate area. Our own Sun, luckily, will never become a supernova, as it doesn't have enough mass. But if it did, there is a good chance that Earth would be either partly or totally vaporized, its rocky outside reaching a boiling point because of temperatures 15 times hotter than the surface of our Sun and being swept away in the path of the supernova's passage. What is surprising, though, is how fast this first wave of destruction would fade with distance. In fact, vaporization is realistically not the biggest danger supernova pose. In 2011, experts from the University of Cambridge figured out that even planets orbiting their star at a distance of 15 billion kilometers, or about 100 times the distance between the Sun and the Earth, would stay in one piece and would instead just be thrown into space, now that there was little left for them to orbit. Of course, such a planet's hypothetical ecosystem would probably have different worries. Things would get very cold very fast. Certainly, even if a planet's crust stayed intact, that does not mean that life on that planet would be sustainable. Ignoring the supernova's light, which can sometimes be brighter than a whole galaxy, leading to blindness for anyone who saw it, just taking away our atmosphere would create big problems. High levels of radiation, even if they did not directly affect us, would change the chemical makeup of our atmosphere, destroying our ozone layer, greatly increasing our chances of dying from radiation poisoning and causing mass extinctions as the effects echoed up the food chain. Scientists put this kill zone at within 25 light years. Beyond that, the power of a supernova starts to lessen as distance makes it use up its energy, although admittedly, the asteroids that might have killed the mammoths came from a supernova that was 250 light-years away. If it happened at all, it was likely due to pure bad luck. Generally speaking, we would not see any damage from a supernova this far away. Its radiation levels would not be high enough to cause mass extinctions. By 500 light-years, we would hardly notice the event at all, other than maybe seeing a brighter star in the sky. This leaves one very important question. Within 300 light-years, are there any supernova candidates we should be worried about? Thankfully, scientists are quite sure that the answer is no. Massive stars are very easy to see, and the only two that are at risk of going supernova are Betelgeuse and Antares, both of which are more than 400 light-years away. White dwarfs are a bit harder to spot because of their lower brightness. They have traditionally been hard to find, making it more difficult to predict whether we might be in danger from them. However, in 2013, ESA's Gaia Space Observatory released a huge amount of information as part of its work to map the stars, which allowed scientists to find 13,000 white dwarf stars within 326 light-years of us. Luckily, despite this big number, scientists are still confident that none of these are about to explode anytime soon, meaning within the next few 100,000 years. Talking about Betelgeuse, some scientists predict that this red giant might explode much sooner than that, maybe within the next few decades. Their research works on the idea that Betelgeuse has a much bigger radius than thought before. But if it is true, it might mean that we would get to see a local supernova in our lifetimes. Of course, according to some models, we would have nothing to worry about. The shock wave moving outward from Betelgeuse would take some time to get to us, and even once it got here, its force would be less than the pressure from the solar wind. In other words, it would not be our magnetosphere or atmosphere that protected us. The protective covering of the sun's heliosphere would be enough to keep such a supernova away. So there you have it, a look at the incredible history of supernova encounters, as well as the advanced research that has come tantalizingly close to proving their impact. While supernova are maybe some of the biggest explosions in the universe, by some lucky chance, our part of the galaxy has nothing really to fear from them. The chance of us being hit by even the nearby stars, like Betelgeuse, that are set to go supernova is incredibly small. It is true that Earth has plenty of its own disasters such as floods, earthquakes, and hurricanes, which can bring ruin to a community in a moment, and space is still a dangerous place. But it is comforting to know that of all the things we have to worry about, we can probably take planetary destruction from supernova off our list. The news in the last few weeks has been filled with talk of the heat waves and wildfires spreading across the world. Temperature records everywhere have been broken, from the USA to the Middle East, Africa, and Japan. Along with this has been the sad loss of thousands of often vulnerable people who could not get away from the extreme heat. Scientists have different views on whether this summer's heat is because of the effects of global warming, but the effect of this heat wave on the world's carbon dioxide levels is undeniable. And today I will walk you through what makes the wildfires happening globally so terrible for our climate, according to NASA research. First, however, I will explain some global warming terms to give you some background for this video. The sun warms the Earth's surface with electromagnetic radiation, much like how your skin gets warm when you are in direct sunlight. This energy is taken in by the Earth's surface and then let out as infrared radiation, some of which goes back into space. You have probably heard of greenhouse gases. These are gases that basically take in some of the infrared radiation in the atmosphere, which warms the atmosphere. The main greenhouse gases are carbon dioxide, methane, ozone, and even water vapor. Water vapor actually causes up to 72% of the greenhouse effect on Earth. That is why on a cloudy day, it can still feel quite warm. The greenhouse gas that often shows up in the news is carbon dioxide, and this is because humans are very good at making it, and we have the biggest effect on its level in the atmosphere. But do greenhouse gases really warm the atmosphere? Well, this is where we can turn to space for a better understanding, which is one of the reasons why space exploration is so valuable to us. You only have to look at our sister planet Venus to see the full effect of a greenhouse gas. Venus's atmosphere is made of 96% carbon dioxide, which raises the planet's average temperature to 462 degrees Celsius. That is even hotter than the daytime side of Mercury, which is much closer to the Sun than Venus. Mercury's temperature on its night side even drops to 90 degrees Celsius when it is not in the Sun, because it has no atmosphere to hold heat. On the other hand, Venus's night side is just as hot as its day side. This is the result of a runaway greenhouse effect. It is thought that Venus might have had a much more livable atmosphere billions of years ago, and even had liquid water on its surface. But as the sun got brighter, the planet got hotter, and the surface water evaporated into the atmosphere, starting a greenhouse effect that warmed the planet even more. This cycle went on until its liquid water ocean boiled away into its atmosphere. This water vapor has since been lost to space, as Venus does not have a magnetic field to protect its upper atmosphere from solar winds. The H2O moves up through convection to the top of Venus's atmosphere, where UV light reacts with it. This reaction breaks down the water vapor into hydrogen and oxygen. The hydrogen is carried away into space, with the heavier oxygen rejoining into carbon and sulfur oxides. 4 billion years later, it is full of CO2, a process possibly also helped by the volcanoes on its surface. Even on Earth, the worldwide temperature would be -1 if there were no greenhouse gases in its atmosphere, so they are, in fact, a vital part of our existence. But the balance of these greenhouse gases is critical for our long-term survival. And have these gases stayed balanced? No. This is a simulation of data from the NASA Aqua spacecraft that shows the rise in atmospheric CO2 from 2002 to 2016. In 2002, the CO2 concentration was about 375 parts per million until we got to 2016, where we were already well over 400 parts per million. One scientist, Dr. David Crisp, explains how CO2 levels have gone up by 20% since he was born, with CO2 already making up around 25% of the greenhouse effect on Earth. And with CO2 emissions showing no sign of slowing, how high will this number go before it levels off? We are already seeing levels that have not been seen on Earth for an estimated 500,000 years or more. But surely Earth has some natural defenses, unlike Venus? Well, in fact, it does. Carbon dioxide sinks are real, and they are mainly the Earth's oceans and forests. Earth has a huge amount more carbon than what is in the atmosphere, but most of it is kept either in the ground, in the deep oceans, or in biomass, which includes trees, phytoplankton, plants, and animals. Let's look at forests at work over 1 year. In 2006, a supercomputer model was able to find the main sources of CO2 production, which are usually large cities. During the winter, trees in the northern hemisphere are not doing photosynthesis, which means carbon dioxide is not being taken out of the air as much. By summer, the levels go down again as the trees start to pull CO2 from the atmosphere into a kind of carbon storage. although oceans and trees throughout the year only take in half the CO2 made by burning fossil fuels and biomass all year, all of which create CO2 as a byproduct. But by the time winter comes again and the deciduous trees lose their leaves, CO2 levels go up again, a little higher than the average for the year before. As I said, the other big carbon sink is the world's oceans. The oceans take in about 25% of the carbon dioxide made by humans through atmospheric carbon dioxide dissolving into the water. One of the ways CO2 is used in the water is by phytoplankton, tiny ocean plants that use photosynthesis to grow. They take in carbon dioxide from the water and let out oxygen, and when they die, they sink to the bottom of the ocean where a large part of the world's carbon is kept. It is not known why, but phytoplankton numbers have also been going down year after year at about 1% per year. This is not good for the overall health of the oceans, as they are the first step in the food chain, feeding everything else in the ocean, either directly or indirectly, but that could be a whole different subject by itself. So CO2 levels are going up. What does that mean for us? Well, some results of a warming world include melting ice caps. Snow is great at reflecting heat from the sun back into space because of its bright white color. Smaller ice caps mean smaller amounts of light being reflected back, and instead, the heat is taken in by the oceans, warming the planet even more. As the oceans get warmer, this can lead to more extreme weather events, including hurricanes and droughts. As oceans get hotter, circulation in the oceans may slow down, making it harder for them to take in as much heat, and especially carbon dioxide from the atmosphere, as the surface becomes less able to dissolve it. In 2009, it had already been reported that the South Indian Ocean is up to 10 times less good at taking in CO2 than thought before, because of a high amount of CO2 at the surface. Right now, the oceans still act as a CO2 sink, but the worry is that they could become a source of it instead at some point in the future. Another result of rising CO2 levels is that average temperatures around the world are going up. Let's compare temperatures from the 1800s, when records started, all the way to today. From this, it is absolutely clear that the world is getting warmer. Closer to today, 2014 was the hottest year on record, then 2016 was the hottest year on record. 2017 almost kept the trend going by being the second hottest year on record, and 2018 might again become the hottest year on record and is currently breaking individual records around the world for the highest recorded temperature ever. And here is the main point of the video. A major result of climate change is that forests and plants around the world are drying out because of drought and heat. This means they are more likely to catch fire. There is a biome on Earth called taiga or boreal, an area that goes across Canada and Russia. It is the second largest biome on Earth after the oceans and is mostly made of coniferous forests. In 2014, a fire tore across a part of the boreal forest in Canada's Northwest Territories, an area the size of Maryland, or 7 million acres. These fires alone let out 94.3 teragrams of carbon into the atmosphere, about 103 million tons. This meant that the single fire let out half as much carbon back into the atmosphere as all the plants and trees in Canada usually take in a whole year. Biomass burning right now makes up 30% of total carbon dioxide production across the world, but the Arctic is warming faster than any other area on Earth, and these fires may get more frequent and intense. In 2016, 8.6 million acres burned in the Russian taiga. And on a direct level, let us not forget about the wildfires that recently happened in Greece, the U.S., and other places worldwide, which have directly brought tragedy to people. The problem with these trees burning is that they release a large amount of the carbon they stored back into the atmosphere. That land will also take a very long time to grow back, as trees need decades to become mature. While these forests are regrowing, their ability to store carbon is not the same as it was before. In 1988, a wildfire went across much of Yellowstone National Park, damaging 36% of the park. Less than 30% of the burned area had forest cover again by 2008. Fires are not the only danger to forests. An increase in natural disasters will also put CO2 into the atmosphere. Hurricane Hugo in 1990 disturbed a huge 4.5 million acre area of forest. This let out a large amount of CO2 into the atmosphere as the trees decomposed. There is a small silver lining, however, to the increase in CO2. The Earth is getting greener. More of the Earth is covered by plants than at any other time in recorded history. The tundra biome is having warmer temperatures, and the higher CO2 levels are giving a boost to plant growth. As a result, more trees and shrubs are growing there. However, this boost may only be temporary. Studies have shown that plants get used to higher concentrations of carbon dioxide, and the strong boost given to plant growth gets smaller over time. There is no question that CO2 and other greenhouse gases are increasing in amount in the atmosphere. There is also no question that the average temperature each year is also going up. This video does not try to solve these problems. I made it just to bring awareness to some of the results of global warming that may even speed up this disastrous process. I must say, my reason to make this video was driven by recent news stories of heat waves and wildfires, and I just felt that global warming was tied to these disasters. After researching, I have come to the conclusion that it is. However, you should know that many processes affect our climate, and I have focused mainly today on the carbon cycle. This is a huge topic, but hopefully I can start a conversation. The sun is a massive, glowing, celestial body, a powerful store of nuclear energy. Every day it lets out billions of tons of electromagnetically charged plasma, sending it into space. These powerful eruptions, called coronal mass ejections, CMEs, are shot into the solar system, creating what we know as solar storms. These highly charged plasma particles rush towards Earth at speeds over 1 million kilometers an hour. And one might think that with the speed and power of these particles, we should all run for cover when they come. However, Earth has natural defenses that stop most of these particles from hitting us. One such defense is the Earth's strong magnetic field, which pushes the particles around the planet and towards its poles. Particles that do get through the atmosphere are taken in and give the energy to drive the climate on our planet. In fact, the sun is vital for life on Earth. For example, it gives just the right amount of warmth and light so that plants can photosynthesize the sun's energy into usable carbohydrates. This energy then moves down the food chain until it gets to us humans. We eat and change food to give our bodies usable energy. Almost all food energy can be linked back to the sun, our life source, and the very start of our food chain. But could the solar system's giant star also bring disaster? How big can these CMEs get? What if the most powerful solar storm ever seen were to hit Earth tomorrow? Could the sun actually hurt or destroy humanity? For a star, our sun is quite stable, a kind of star casually known as a yellow dwarf. It is middle-aged and has not had dramatic changes for the last 4 billion years. We can be thankful that our sun is as stable as it is, as unlike most other stars, the energy it gives out is fairly steady. If you were to watch video of the sun taken by the Solar Dynamics Observatory, however, you would soon see that even one of the most stable kinds of stars shows a dynamic scene of activity. Sunspots, solar flares, and coronal loops are on the sun's surface every single day. One could even say the surface looks almost like a liquid. But the sun is not solid, liquid, or gas. Instead, it is a giant, nearly perfect ball of plasma, made mostly of hydrogen and helium. At the sun's core, because of its huge mass, nuclear fusion happens. In the sun's core, hydrogen atoms are fused together under great pressure to become helium. The sun itself, I like to think of it as an onion, basically made of different layers. So in the core, the very middle of the sun, that's where nuclear fusion happens. Now you have to picture, so basically, the sun is a kind of huge bowl of plasma, a soup of particles, ions, atoms, electrons, everything mixed up together. On average, it takes a photon to move through the radiative zone, something like 170,000 years. Yes, it's basically incredibly dense, and then from that, it then gets to the convective zone. So everyone knows that hot air goes up and cold air goes down. So what then happens is the material is very hot at the bottom near that radiative zone, and then it expands and it rises to the surface. And that's the main way heat moves from that point on. Of course, then glowing from the surface like any hotter material does. Plasma is a very good conductor of electricity and is also greatly affected by magnetic fields. So sunspots are actually the surface sign of the magnetic fields of the sun. So the magnetic fields actually get very tangled under the surface between that radiative zone and the convective zone. The magnetic poles get tangled. They usually show up in pairs, in groups. If you think of a magnet, you have positive polarity, negative polarity. That's usually seen in a pair. One would be positive, the other would be negative. And usually the strongest magnetic fields that we see are in the sunspots. Sunspots can be anywhere from about 15 kilometers in size to around 160,000 kilometers, so many times the size of the Earth. Sunspots can often be seen at the bottom of different solar events. Coronal loops, large rings in the sun's atmosphere, prominences, large, bright, gassy features reaching out from the sun's surface, going into space for thousands of kilometers. And solar flares, a sudden increase in the sun's brightness and temperature. Solar flares usually happen over active regions, and active regions are basically sunspot groups. So these are the places where we definitely see the strongest flares. A reconnection event is basically what makes the energy that causes both flares and CMEs. Because the convective zone is basically very turbulent, many of the current simulations show that most of the magnetic field as it goes up through the convective zone is basically being destroyed, kind of being spread around. It's more complex magnetic structures like twisted magnetic fields that tend to survive, and so you can imagine, especially over large sunspot groups, we do see very complex magnetic field setups. Magnetic fields so twisted, basically making these complicated geometrical, topological structures, and it's inside those structures that magnetic fields and magnetic energy are stored. And what happens during reconnection? I usually describe it like a rubber band. So you twist it, turn it, and then basically at some point you pull it too hard and it snaps. And that's basically when we have the reconnection event. And what happens during the reconnection event? Basically, as the name says, the magnetic field lines reconnect. And when that happens, you get a lot of energy being let out on the order of millions of nuclear weapons, nuclear bombs, all at once. And that energy will make both solar flares, where a large amount of radiation is let out, and also possibly lead to large-scale movement of the material that was held in the prominences, both towards the sun and away from the sun. When that reconnection event occurs, then again, the material which is held in those magnetic fields normally will move one way or another. A lot of it will move back towards the sun, often following those magnetic field lines, so moving to the footprints, like for instance, moving to the sunspots, if that's where the footprints are. But equally, in the middle of those magnetic fields, quite often a bubble of material is basically shot away from the sun. And so, what you'll end up having is millions of tons of charged material flying out from the sun relatively fast. I mean, on the order of hundreds of kilometers per second to thousands of kilometers per second, and those are what we call CMEs, coronal mass ejections. These CMEs are always interacting with planets. Venus, when it faces a CME, has its lighter particles stripped away in the upper parts of the atmosphere by the force of the ejection. This leaves the planet with only the heavier molecules, a toxic smog that, as far as we know, cannot support any life. Earth would have a similar fate if it were not for its fairly strong magnetic field. Particles from a CME aimed at Earth are redirected around the planet because of the Earth's magnetosphere. Some particles are sent to the Earth's poles, where the charged particles hit the Earth's ionosphere, causing the beautiful aurora borealis and australis. Thanks to a mix of the Earth's magnetosphere and atmosphere, we are totally protected from all kinds of particles space tends to throw around. Or are we? When the Earth is hit by a CME, this is called a geomagnetic or solar storm. When a solar storm hits us, Earth's magnetic field gets somewhat squashed by the force of the CME for as long as the storm lasts. Normally, this would not, and has not, been a problem for people with their feet on the ground. But what would happen if the most powerful solar storm ever seen were to hit Earth today? To find what is thought to be the most powerful CME in recorded history, we have to go back to 1859 to a solar storm known as the Carrington event. From August 28th to September 2nd, 1859, many sunspots showed up on the sun in one area. On August 29th, southern auroras could be seen as far south as Queensland, Australia, meaning a solar storm was already happening. Before noon on September 1st, amateur astronomers Richard Carrington, who the event was named after, and Richard Hodgson separately saw and recorded an extremely bright solar flare. Carrington and Hodgson on their own wrote reports, both of which were later put in scientific journals. The flare was connected to a major coronal mass ejection that went directly towards Earth, taking only 17.6 hours to travel the 150 million kilometer journey, much faster than the speed of typical CMEs. Usually, a CME would take several days to get to Earth. It is thought that the high speed of this particular CME was helped by a previous CME, maybe the cause of the large aurora event on August 29th in Australia, which would have cleared any ambient solar wind plasma for the Carrington event, like a giant slipstream. With this slipstream in place, the path was clear for the largest CME known to humankind. On September 1st to 2nd, 1859, the largest recorded geomagnetic storm happened. Auroras were seen all over the world, across the entire northern hemisphere, as far south as the Caribbean. The aurora over the Rocky Mountains in the U.S. was so bright that its green glow woke up local gold miners who started making breakfast, thinking it was morning. It was said that because the aurora was so bright, people in the northeastern United States could still read a newspaper. The aurora was seen as far from the poles as sub-Saharan Africa, Mexico, Queensland, Cuba, Hawaii, and even at lower latitudes, very close to the equator, such as in Colombia. This is unheard of, as usually auroras are not seen at middle latitudes. By September 3rd, the aurora in the sky was said to be the brightest and most magnificent it had ever been. However, though beautiful, this storm brought unexpected problems. A result of the geomagnetic storm was that the electrically charged particles from the sun rushed through telegraph systems all over Europe and North America, making them not work, and in some cases even giving electric shocks to the telegraph operators. Telegraph pylons gave off sparks from the charged atmosphere, and amazingly, some telegraph operators could still send and receive messages even after they had unplugged their power supplies. The storm was like a hemisphere-wide EMP, electromagnetic pulse, bomb, fairly harmless to humans but very bad for electronics. The force of the CME in 1859 was so strong that it squashed the Earth's magnetic field all the way down to its atmosphere. Because North America and Europe were facing the sun at the time, these parts of the world were most badly affected by the first impact of the CME. Looking back at geomagnetic storms since the 1850s, there have been a few that were big but not catastrophic. For example, in March 1989, a CME hit Earth, making satellites unusable for several hours and jamming radio stations in Europe. Power in Quebec was out for about a day. Some people there wrongly thought the Soviets were attacking and that the glow in the sky was from nuclear bombs. Thankfully, however, this solar storm and many others like it did no lasting permanent damage. Today, if a CME the size of the Carrington event or bigger were to hit Earth, the results would be much more disastrous than they were for humanity in the 1800s. Technology was just starting back then, whereas today, we have satellites in space, computers, telecommunications, and power plants that would all be seriously damaged in such an event. Because of the wide range of a solar storm, it would greatly affect equipment over a huge area, with the most at-risk technologies being the electricity grid and telecommunications, which have cables spread out over long distances. Without proper protections in place, transformers on the power grid could break, and millions upon millions would be without power for a long time. If transformers were damaged, for example, it would take years to replace them, as transformers need years to make. Often, these transformers are custom-made for specific needs and are not mass-produced. Without power, refrigerators would not be able to stop food from spoiling, and as the transport system would also be out of action, since fuel stations need electricity to pump, replacing that food would be a problem. Payment systems that rely on credit cards would stop working. People would not have access to the internet, as computers would have no power, and battery-powered devices would quickly run out. Radio and TV stations would be down. Hospitals would have trouble when their backup generators ran out of fuel. We would be totally cut off from the outside world. The world is simply so reliant on technology, and especially on electricity, that it is feared we have lost the ability to work as a society without it. And worryingly, it is our power grid that is most at risk from a supersolar storm. An independent think tank recently guessed the cost of damages to the USA alone at $2.6 trillion, which would ultimately destroy the economy. And unfortunately, that does not include the social effect it would have. As is often true in natural disasters, some people would surely go back to more primal instincts, with attitudes like every man for himself. Chaos, looting, and a disregard for the law could follow. This would only get worse the longer the population is without communication from their government or an authoritative group. Hopefully, in such a situation, the basic goodness of mankind would win, but it is a believable scenario. The think tank guessed the recovery time to fix the damage from a CME at 4 to 10 years and predicted that 2/3 of the U.S. population could die from starvation, disease, and chaos during that time. We only need to look at a couple of examples to understand how serious the situation is. In 1989, Quebec had a big solar storm that made its power grid fail in just 90 seconds. This problem was made worse by the fact that it was winter, where temperatures can drop well below freezing, leaving vulnerable people in a possibly very bad situation. It took 9 hours to get power back, and total costs from the disruption were estimated to be around $2 billion Canadian dollars. From a social point of view, we only need to look at Puerto Rico, which, at the time of writing this script in early February, is still without power for 40% of its people. That means it has been without power for 140 days, and it is thought that it still needs 50,000 utility poles and roughly 10,000 kilometers of electricity cables. If a solar storm were to hit, it would not just be an island that is left powerless, it would be a whole hemisphere. And Earth has had some very close calls. A Carrington-sized event could have happened in 2012, when a huge CME was shot out from the Sun. This was the largest CME that has been recorded with modern technology, and it directly hit one of the stereo satellites that was watching solar activity. It is the charged particles that cause this distortion effect. Shortly after this solar flare, had it hit Earth, the hypothetical disaster scenario could have come true because of a lack of historical evidence. We have no way to predict when the next major CME could hit Earth. As far as we know, a CME even larger than the Carrington event could hit us tomorrow, or the next one could be in a few thousand years. But what plans does the world have in case of such an event? Since 1995, NASA has had a telescope in orbit that is always watching the Sun for CMEs. As light travels much faster than the speed of a CME, this would give us about 17 hours of warning before the CME hits Earth. If everyone acted fast enough, this might be enough time to shut down some power stations, which would protect the electricity grids. This is known as the Solar Shield Program, and amazingly, the U.S. is currently the only country to have such a program. Countries are also working on temporary transformers, which are faster to make. Additionally, nations throughout the Western world are currently in the process of proposing upgrades to their power grids that would stop an electricity surge caused by a geomagnetic storm from destroying the network. This process, however, is slow and held back by bureaucracy. It seems countries are in no hurry to pay the cost of upgrading the infrastructure. These measures to protect the power grid are not yet in place everywhere. It also seems that most people in the world do not know about CMEs, instead fearing much less likely scenarios like an asteroid hitting Earth or alien invasions. Humanity as a whole is shockingly unprepared for a natural disaster caused by a super solar storm. George H. Baker, Professor Emeritus from James Madison University, spoke to the House Committee on National Security in the United States and gave this reason for the lack of progress being made. He said, "To a major extent, the lack of progress in protecting our most critical infrastructure to solar storms is that the responsibility is distributed. There is no single point of responsibility to develop and implement a national protection plan. Nobody is in charge." When I asked the North American Electric Reliability Corporation about EMP protection, they informed me, "We don't do EMP, that's a Department of Defense problem." The Department of Defense tells me EMP protection of the civilian infrastructure is a DHS responsibility. DHS explained to me that the responsibility for the electric power protection is within DOE, since they are the designated sector-specific agency for the energy infrastructure. And this is, sadly, from one of the most progressive countries in the world on this subject. And until humanity is ready for a CME, we truly are at the mercy of our life-giving star. Are we the final technologically advanced civilization that will ever arise on Earth? It's a real possibility. Humanity has climbed to the top, becoming the dominant species on our planet with a population of 8 billion and growing. We have airplanes, cars, robotics, advanced computers, and the ability to send our spacecraft to other worlds, and perhaps soon we will even travel there ourselves. Yet Rome wasn't built in a day, and it wasn't built without a significant cost. It has taken billions of tons of coal, oil, and natural gas to power the industrial revolutions that have shaped society into what we see today. Those resources are finite, and they will take millions of years to be created again. Which brings up an interesting question. Was this a one-time chance? If something were to happen to civilization, if some major disaster or nuclear war sent all of us technologically back to the Stone Age, or even wiped us out entirely, are there enough resources left for a future civilization to rebuild? Or are we now the first and last civilization born on our Earth that will ever try to reach for the stars? And if that's the case, why? Today we will look at the rise of our technologically advanced society and find out what materials are needed to build what we have now. And then we will see how much of those essential ingredients are still available. But for the purpose of this thought experiment, let's start by pressing the doomsday button right now. Boom! In a single decisive moment, humanity has been sent back to the Stone Age. All technology has been destroyed, maybe in a terrible nuclear war. Human society has fallen apart. Whoever is left is now faced with rebuilding civilization in a world with no buildings, machines, books, and perhaps worst of all, no internet. Let's imagine, for this thought experiment, that natural resources are unharmed, but nothing can be saved from the civilization that came before. Like the ultimate survival game, everything has to be made from the beginning. Once our survivors get over the first shock of this frightening new reality, they will quickly see that they need at least 3 basic things if they want to survive: food, clothing, and shelter. Luckily, these are all things you can get from different renewable sources. These will not be the things that stop them from rebuilding civilization. With wood, you have materials for building. Wool or cotton can be woven into clothes. Animals, vegetables, and fruit can be hunted and gathered for food. Conveniently, you can get these natural resources with very simple tools: sharp sticks for hunting and fishing, and basic axes and knives for chopping and shaping wood made from nothing more than sharp stones tied to sticks with hemp and rope. With this as its start, a civilization that comes after us could absolutely and easily create a thriving hunter-gatherer society. We should even be able to move beyond that, although if our civilization is ever to reach for the stars again, they will have to start by moving from stone tools to bronze and iron. For bronze, an alloy made by mixing tin and copper, fires made from wood will be enough. Metal ores taken from the ground need to be heated to separate the rock and other unwanted materials. Smelting tin needs temperatures of 230 degrees, and smelting copper needs just under 100 degrees. Luckily, a large bonfire made from wood can reach temperatures of 1,100 centigrades, which makes bronze just within reach for our new civilization. But it is with iron that the problem becomes very clear. Iron is tough. While this metal is very common in the Earth's crust, its melting point of 1,583 means our new civilization would have to do more than just put it on a wood bonfire to be able to smelt it. Luckily, there are ways around this problem. By partially burning wood in low oxygen conditions, you can make charcoal, which burns at a higher temperature than the wood it came from, because the first cost of combustion to get rid of all that water and sap has already been paid. This can be made even better by putting your fire in a kiln and controlling the airflow. With the right airflow, even a wood-burning fire can get to temperatures of 1,500 degrees Celsius, like with the record-breaking Sungan snake kiln in Taiwan. However, using charcoal has a price. You need a huge amount of forest if you want to get enough to support a metal-hungry civilization. It will need to be replanted often, but more importantly, you won't be able to turn that land into farmland, something your civilization will also need if it wants to grow and develop. This is why most countries use fossil fuels to make their steel. Coal or methane gas can be used to make incredibly hot fires, without making you give up your farmland. You might be wondering if our new civilization could get by without these fossil fuels. If we just grew a little more slowly with a smaller population, couldn't we make charcoal work? Charcoal is carbon neutral, as the trees that make it grow by taking carbon from the atmosphere. Couldn't a new civilization reach our level and get to space again without using fossil fuels in their production? The answer is no. The lack of fossil fuels would be devastating to a civilization trying to reach for the stars. This may be a hard thought to accept, but just think for a moment about how much our own civilization uses coal, oil, and gas. Now, I am not saying that we don't need to do better just because we currently use a lot of fossil fuels. As a species, that doesn't mean we shouldn't try to use less and take better care of the planet. At the end of the video, I'll talk about Planet Wild, a channel that goes into that in more detail. When we talk about using fossil fuels, it is easy to think of them only in terms of making electricity, which our new civilization would need to achieve if it wanted to go back to space travel. To be fair, fossil fuels are still the world's main energy source. In 2022, 83% of the world's energy came from these sources. But fossil fuels are also incredibly important in making 4 other vital ingredients for our civilization. I have already mentioned steel, for which our current global need is 1.8 billion tons a year because of its strength and durability as a building material. But there is also concrete, plastic, ammonia, and silicon. Can you imagine a world without concrete? Without fossil fuels, you would probably have to. The sand and gravel that make up concrete are easy enough to get, but the cement that holds it all together, made from a mix of limestone and clay, needs temperatures of 1,400 to properly fuse them. If our new civilization wanted to make concrete, which would be useful as it is a very malleable, durable building material, good for building a spaceport for launches and many other buildings and platforms, they would need to find a fuel that could burn at that temperature. The civilization that comes after us would need a huge amount of charcoal to fill the gap if fossil fuels were no longer available. But that is not even a choice for silicon. Silicon has many uses in our society, from ceramics to brickwork, but by far its most important feature is that once it is refined and purified, it is the element used to make computer chips. Thanks to how common it is and its properties as a semiconductor, it is very easy to find in its raw form. However, refining it is a complex process that needs temperatures of 2,350 degrees Celsius. Charcoal does not burn that hot. It is not for no reason that the last 100 years have been called by some the Silicon Age. Can you imagine our world without computer chips? In terms of getting to space, the computers that guide and control the launch of a rocket would certainly have a hard time without computer chips. There is more. Ignoring materials that just need high heat for smelting or refining, fossil fuels are literally a building material we use to make our products and feed our population. While we sometimes worry about the amount of plastic being used in the world, there is no denying how important it is to modern civilization. It is used to make keyboards, boxes, sterile tubes, and syringes for medical uses, polyester clothing, car bumpers, and wind turbines. Yes, even green energy sources like wind turbines are made from materials that need fossil fuels. A wind turbine is about 70% steel and 10% plastic, both of which rely on fossil fuels. Plastics are also used in rocketry. Having a lightweight material that is easy to mold, fairly stiff, and above all light, is very helpful for rockets that are trying to get rid of every gram of weight for launch. Launching without plastics makes rockets much heavier, needing more fuel or smaller payloads. Finally, let's think about ammonia. While you might think we could get by without plastic in our lives, without ammonia, it is likely that about half of the Earth's current population would die from starvation, which, while not directly related to reaching space, is a rather big problem in itself. Ammonia is used in fertilizer. Although other natural fertilizers exist, they don't have the power provided by ammonia. Without ammonia, we simply would not be able to keep up the level of food production needed to support the global population, not by half. And ammonia is made from methane, which is mostly gotten from natural gases. When looked at this way, it is easy to understand the size of the challenge that would face a civilization trying to reach a technological level where they could explore space if they did not want to or did not have access to fossil fuels. And let's be honest, the most easily accessible fossil fuels on Earth are now mostly gone. You need serious equipment to get to the fossil fuels we are currently taking out, which needed fossil fuels in the first place to build our civilization. Our civilization has been built on the foundation of fossil fuels. They give us our plastic, our steel, our concrete for our buildings and our energy. Without them, we would struggle to make the metal for a rocket or the fuel that powers it, along with the computers that guide it. And so, for our thought experiment, how much fossil fuel have we used, and is there enough left so that the civilization that comes after us could do it again if they absolutely had to? It is hard to find estimates that clearly show how much fossil fuels have been used up by now. Our current use is about 15 billion metric tons per year, although this number has been going up for some time, so it will likely keep climbing as our population grows. However, by projecting our current use backward over the past, and by considering the increase in demand over time since the 1800s, when the Industrial Revolution mostly started, it is possible to get a ballpark estimate of 750 billion metric tons of fossil fuels used by the human race to get to our current state. This is figured out by multiplying our current yearly use by the number of years between 1800 and now, and then roughly quartering the result to show that demand was much lower for most of that time. Now, we don't know exactly how much fossil fuels we have left. Current estimates, based on proven reserves, suggest that we will start running out of fossil fuels in just 50 years. Coal will last longer. Coal reserves should keep electricity going for up to 130 years, but oil and natural gas could possibly all be gone within the lifetime of people alive today. Calculating based on our current use, this adds up to at least another 750 billion tons of fossil fuels left, the same amount that brought us to this point, only we are currently using it much faster. Of course, this number could be much higher. This estimate is based only on proven reserves. If more oil fields are found, or if technology is developed that lets us get to fossil fuels more effectively, the amount of fossil fuels available on the planet could be much greater than current estimates. Still, this is enough information to give us our answer. A civilization that comes after us would indeed have enough resources to reach the same technological level that we currently have. However, they would likely find it much harder, as much of those untapped fossil fuel reserves are buried at much greater depths than the ones our own civilization found. We have used up the supplies that were easy to get to. In 1950, the average depth one had to drill to get oil was 1.1 kilometers. This now is at 1.8 kilometers, but some oil and gas fields are as deep as 9.1 kilometers. It would not be easy, but the resources are currently there, for now. If we ask this question again in 50 years, we might get a different answer. It might be necessary for future civilizations to get used to the idea of a more comfortable farming existence. Nevertheless, if there is a bit of hope to shed on this, it is that necessity is the mother of invention. The materials we use are the best at what they do. But that is not to say that with enough determination, a new civilization that comes after us could not again reach for the stars, even without fossil fuels. They might need to move more slowly, their population might never reach our levels, and many would have to make do with cruder tools or less than ideal materials. But where there is a will, there is a way. Perhaps the future civilization will one day get methane from biowaste. Methane can be used as rocket fuel. Without fossil fuels, the civilizations that come after us would look very different from our own. They would have different priorities and would perhaps use their land with a different focus in mind. But perhaps they could reach the stars in their own special way.